So we've seen that with algorithms that are recursive, such as merge sort, we automatically get a recursive description of the running time. So more generally, we have a sequence of numbers, which may or may not be describing the running time of an algorithm, and the value at n is determined by the previous values. For example, we've had the Fibonacci numbers, we've had something to do with merge sort, and we could multiply these examples forever. In general, f of n is just something involving the previous values, some function, in fact, some expression typically in the previous function values. And typically this is not true for all n, but it's true for some n past some point. So there's a threshold, and before that we have to specify the values in some other way. Those are called the initial conditions. So for example, for the typical Fibonacci recurrence, we know that we need to define the first two numbers, and then if n is greater than or equal to 2, we then define the sequence recursively. So we have the initial conditions, and beyond that a recursive description, and that's enough to define it uniquely. So it's defined. We could calculate any value by using the recurrence, as we've seen. However, what we're interested in here is some analytical solution for these recurrences, some kind of simple formula for the nth term, rather than just a way of calculating it. Now I'm going to present two simple methods for solving these recurrences, both of which rely on the principle of induction in some sense. We're going to look at the recurrence from the bottom up or from the top down. Those are the two ways. And either way, we're going to see a pattern that arises when we repeatedly apply the recurrence to itself. So let's start with a straightforward example. T of n is 2t of n minus 1 plus 1. That's if n is greater than or equal to 1. And we need the initial condition that t of 0 is equal to 0. So I'm first going to look at the bottom-up method. So we know that t of 0 is 0. T of 1 is 2t of 0 plus 1, which is 1. T of 2 is 2 times the last value plus 1, which is 3. T of 3 is 2 times the previous value. And I think you can see a pattern already. I'll do one more. T of 4 is 2t of 3 plus 1. That's 2 times 7 plus 1 is 15. So from this, we can guess a formula. Just stop the video for a few seconds and think about what that formula is going to be. I'm going to guess that it's close to a power of 2. This is 2 minus 1, 4 minus 1, 8 minus 1, 16 minus 1, and in fact it's 2 to the n minus 1 is what I'm going to guess. Check that against those first few values of n and you'll see that it fits. Now, that's our guess. We should prove that. We'll prove it by mathematical induction. So n equals 0. If n equals 0, we have 2 to the 0 minus 1 equals 0, and t of 0 is equal to 0. So that's good. Everything works there. And now we suppose it's true for some n, some arbitrary n. We want to show that it's true for n plus 1. So then we can assume by the inductive hypothesis that t of n is 2 to the n minus 1. Now replacing n with n plus 1 in the definition here, since it's arbitrary, I get 2t of n plus 1. That's just from the definition of the sequence. Using the inductive hypothesis here, I can feed in that expression, doing the algebra, expanding it out, I get exactly the formula that we wanted. We get the same expression here, but with n replaced by n plus 1. So that finishes it, and by induction we have what we wanted. So in the case where you have a reasonably simple formula that you can guess, this bottom-up method works quite well. For the kind of recurrences that we have in a course like this, it works quite well for a reasonable number of them. Now I want to do the same example from the top down instead of from the bottom up. So remember the recurrence that we had. Looks like this. So now the idea is that we apply the recurrence to itself from the top down. So t of n is 2 times t of n minus 1 plus 1. Let's assume n is big enough that we're not at the boundary condition or the initial condition. So we can use this recursive definition. Now let's assume that n is at least 2 so that we can apply it twice before we get to the initial condition. So it's 2 times, now, t of n minus 1, I can plug in minus 1 in here instead of n, as long as n minus 1 is at least 1. And I'm going to get 2 times t of n minus 2 plus 1 from this part. And I still have a plus 1 over here that I need to remember. And when I expand this out, I'm going to write it like this because I want to see a pattern later on. It doesn't really matter how you do it, but I won't do all the simplification. We'll keep it like that. And in fact, we can keep doing that. So let's assume n is at least 3, for example. T of n minus 2 is 2 times t at 1 less, which is n minus 3, plus 1. And then I've still got to add the 2 plus 1. But when I expand that out, I get 2 cubed t of n minus 3 plus 2 squared plus 2 plus 1. And I think you can see here that we're going to have a formula we can guess. If I keep doing this, say k times, what I'm guessing is it's going to be 2 to the k times t of n minus k. If you look at the last few, you'll see this pattern coming up. 2 to the k times t at n minus k plus some sum of powers of 2. 2 to the I equals 0 to k minus 1. Here k was 3, we summed up to 2. Here k was 2, we summed up to 2 to the 1. Here k was 1, we summed up to k to the 0. So that's what we get, and then it's just a matter of evaluating that. That's true if n is greater than or equal to k, say. for every k. Now if I were doing an exam question, I would just assume that that formula is correct. It seems too simple to get wrong, but let's do it formally by induction just to make sure. So we're claiming that t of n is 2 to the k t of n minus k plus the sum I equals 0 to k minus 1 of 2 to the I. Whenever k is between 0 and n. Obviously if k is bigger than n, we can't do that because t of a negative value is not defined. So let's claim that. Well, we're going to prove by induction. K equals 0, obvious. K equals 0, this sum is equal to 0. It's a sum with no terms in it, so by convention it's equal to 0. This would be 1 times t of n, and this would be t of n, so it's trivially true by definition. So now, suppose that 0 is less than or equal to k, which is less than or equal to n, and I want to be able to say it's true for k plus 1, so I also need that. So k's between 0 and n minus 1 is what that turns out to be. I don't want to run into the boundary and have problems there. When k is equal to n, I can't apply this one more time. But I don't need to, actually. I only need to know that if I have it at a certain value of k, I can go one more. And when I get to n, I can stop. And I am going to stop when we get there. So we can assume, so suppose that this is true, then by inductive hypothesis, we can assume that we have this formula as we have up there. And all we do is just do it one more time, okay? Just as we did over here. So it's 2 to the k times t at some value. T at some value is by definition 2 times t at a value 1 smaller plus 1, as long as we have the correct value here. So what we want is that n minus k, which is what I want to apply it to, has to be greater than or equal to 1. Okay? Well, that's this thing here. If you rearrange this to the other side, you get that n minus k is greater than or equal to 1. So everything's working. We're not running into the boundary. And so it's 2 times the value 1 less plus 1 plus the sum over here, which I haven't changed. Now rewriting that, I get 2 to the k plus 1. I want to write everything in terms of k plus 1. T of n minus, k plus 1, that works well. I've got this sum here, which is the sum up to 2 to the k minus 1, and then I get another 2 to the k over here. So I actually get the sum I equals 0 to k, which I'm going to write as k plus 1 minus 1, 2 to the I. So by induction, the result's going to hold. So that was just dotting all the I's and crossing the T's there to make sure that we have it completely precise. Right, so now's the time to wake up again after we've done that proof, and just to use the formula that we have over here. That's true for n being greater than or equal to k. If I put n equals k, what am I going to get? In other words, I go as far down as I can, take as many iterations of this recurrence as possible. And putting n equals k over here, I get t of n is 2 to the n t of 0 plus the sum of 2 to the I is 0 to n minus 1. Now since t of 0 is equal to 0, I drop that first term and I simply have this sum. Now that's a different formula from what we got before, but it is an explicit formula. But we know that this expression, of course, simplifies like that. It's the sum of a finite geometric series, and even if you didn't know that amount of theory, you would know just from basic knowledge that that's what happens when you add powers of 2 like that. You always get just one less than the next power of 2. So now we've looked at the same problem from the bottom up and the top down. And there's no real difficulty using either of them in practice, and it's up to you which one you want to use. Either way, to do them really rigorously, you need to use induction. If you just want to get an answer that looks reasonable, sometimes it's easier to do it from the top down. The answer comes out in a nice form. In this case, it was reasonably simple once you did the algebra. Sometimes it's easier to guess going from the bottom up. So let's have a look at one more example. The original one, which we called the merge sort recurrence. This is when n is at least 2 and t of 1 is equal to 0. That's the simplified merge sort recurrence where we don't have to worry about floors and ceilings. Let's see whether we can solve this one. Well, this is a bit more tricky than what we've seen so far. We can do this from the top down. You could actually try it from the bottom up as well. I'll leave you to do that. What I'm going to do though first is to simplify in a way, well, I think it's simpler. So first we're going to apply a change of variable, because I'd rather deal with recurrences where we're subtracting in here instead of dividing. So I'm going to make a change of variable here. Since we're only dealing with powers of 2, we can write n as 2 to the k, where k is some non-negative integer. So I'm going to write u of k, by definition, is just going to be t of n. In other words, I'm going to think of the running time as a function of k instead of a function of n. Now, why does that help? Well, it simplifies the recurrence, I think. We're going to write u of k on the left-hand side here. Now, if n is 2 to the k, then n over 2 is 2 to the k divided by 2, which is 2 to the k minus 1. So this expression here can be just written u at k minus 1, because it's just 1 less power of 2. And then I'm going to add an n, which is 2 to the k. And this is true if k is greater than or equal to 1, and u of 0, which corresponds to t of 1, is equal to 0. So now I have this new recurrence, which is equivalent to the first one. Contains all the same information, it's just a change of variable. Now this is pretty similar to the one we just did. There we had a 1 on the right hand side, now we have a 2 to the k. It's slightly more complicated, but not too bad. I'm going to do it from the top down. U of k is 2u of k minus 1 plus 2 to the k. I'm going to do it again. U of k minus 1 is 2u of k minus 2 plus 2 to the k minus 1, and then I still have a 2 to the k here. And when I multiply that out, I get 2 squared u of k minus 2. I get a 2 times 2 to the k minus 1, which gives me a 2 to the k. And that gives me 2 lots of 2 to the k. I'm writing it like that for a reason, because next time you'll see a better pattern. I now go down to k minus 3, and I have to add 2 to the k minus 2 there. And one more step makes it completely clear what's going on. Doing the algebra here, I get 2 squared times 2 to the k minus 2 is another 2 to the k. Right, so now you can see a nice formula, and I'll keep going all the way down so that this power goes all the way down to k. I'm going to get 2 to the ku of 0, which is going to be 0 from our initial condition. And here I'm going to go down as many times as I went down here, which is k. This thing's independent, this 2 to the k is independent of the power here, the number of times I've iterated. It only depends on this left-hand side. So actually I get to that. Now finally, since t of n is equal to u of k, it's k times 2 to the k, but n is 2 to the k, so there's definitely an n factor there. Now what's k? Taking the binary logarithm of each side, I get k on the right and log n on the left. K is log n. That's what it means for n to be 2 to the k. It's just another way of writing that. So the solution to that simplified merge sort recurrence is very simple. It just says that t of n is n log n. And this has great implications for merge sort, because if you have a list of n elements, in the worst case, we've already seen you're doing no more than this number of comparisons. So we have a sorting algorithm that runs in time in order n log n in the worst case. That's a big improvement on what we saw with insertion sort and selections. Right, we're at the end of the recurrence lecture, so here's a few questions to think about. First, what happens if I don't do the change of variable that I did to convert from a multiplicative recurrence to an additive one? If you just leave it as a multiplicative one and do it, it's possible to do. How does the algebra work out? Try and do that yourself. By the way, a common term that you might see in textbooks is telescoping. That's the kind of general procedure that's being used to solve these recurrences. Next question relates to some of the simplifications we made. We assumed that n was a power of 2, so we didn't have to deal with the floor and ceiling functions. But in general, for general n, you do have to deal with them. Now you would imagine that it wouldn't change the solution that much. It's probably going to change the exact solution. But if we only care about the asymptotic order of growth of the solution, whether it's n squared, n log n, that kind of thing, it shouldn't make a difference. But is that the case? That's the next thing to think about. Try some examples. Final question. I dealt with very specific types of recurrences that are occurring in divide and conquer algorithms, but we already saw an earlier recurrence, namely the Fibonacci recurrence. Some of you may already know a solution to this and could easily look it up, but it's worth trying if you haven't before to see why the techniques that we use so far are not going to work to solve that. Or maybe they are. Try them out. Next lecture we're going to deal with quicksort, and we'll see you then.